Here is an explanation for the answer to final exam question number 60, found on pages 673 and 674 of Teach Yourself Electricity and Electronics, 5th edition. We're talking about a transmission line connected to an antenna and a radio frequency transmitter. Again, that's what XMTR stands for, as transmitter. Some texts, you'll see it abbreviated as TX. Now let's suppose, to begin with, that this transmission line is perfectly matched. That means that the antenna is a purely resistive impedance that exactly matches the design impedance of the transmitter and also exactly matches the characteristic impedance of the transmission line. In a typical communications system, for example a CB or ham radio, the antenna will have a 50 ohm purely resistive impedance, and therefore the characteristic impedance of the transmission line will be 50 ohms. The transmitter is designed to operate into a 50 ohm, all purely resistive. In that case, the transmission line is said to be perfectly matched, and the standing wave ratio is 1:1. In effect, meaning that there are no standing waves on this line. Under those conditions, the transmission line is going to exhibit a certain amount of loss anyway. It's not going to convey the signal from the transmitter to the antenna perfectly, because the conductors in the transmission line have a certain amount of resistance, and the dielectric material between the conductors in the transmission line causes a certain amount of loss when voltage appears across it. That's known as dielectric loss. The current loss is the conductor loss. So we're going to have a certain amount of loss in that transmission line, no matter how well we match the antenna to it. But now let's suppose that we have a mismatched antenna. Let's say that we have a standing wave ratio on this antenna of 6:1, something pretty high. 6:1, we might have, say, a 300 ohm pure resistance for this antenna, 50 ohm characteristic impedance for the line. If we have a mismatch that bad, we're bound to get some significant standing wave ratio loss. That, also known as standing wave loss, will manifest itself as true power. The correct answer here is B, as in Bravo. And by true power, what we mean to say is that that loss will actually represent power that never gets out into the airwaves. It's not imaginary power, it's not reactive, it is true power, and it happens for two reasons. The increased standing wave ratio means that the current and the voltage on this transmission line are such that the current loss in the conductors is greater than it would be if the antenna were perfectly matched, and the dielectric loss in the transmission line is also greater than it would be if we had a perfect match. And those losses, those power losses, actually manifest themselves as heat in the transmission line. So that is real power, or true power. We really lose something. Now, that said, a great deal has been made about standing wave ratio losses in transmission lines, and leading a lot of people to go to great lengths and great inconveniences to try to attain a perfect match, or an SWR, standing wave ratio, way down close to 1:1, when in fact, for all intents and purposes in practical situations, A 2-to-1 SWR won't produce enough transmission line loss to make any difference compared to a perfect match. Not any practical difference that any receiver would be able to detect. However, well, that's just a practical versus theoretical consideration. Whatever loss we get because of standing wave ratio in a transmission line, and in fact whatever loss we get in a transmission line, is going to show up as true power. So again, the correct answer to this question is B, as in Bravo.